There is a very important consequence of the CLT that is usually called de Moivre-Laplace theorem, after two French mathematicians. So this theorem states that if X follows a binomial distribution with parameters n and p, then random variable x minus np divided by the square root of n times p times 1 minus p converges in distribution to a normally distributed random variable. So you see that the right part of the formula is the same as here, so that z is a random variable that follows standard normal distribution. And actually the left part is also very close, as maybe you remember that np is the expected value of a binomially distributed random variable, and n times p times 1 minus p is the variance of a normally distributed random variable. So as we see here, that the expected value is subtracted and then we divide by the square root of the variance, here we do the same. But why? So why do we say that this is a consequence of the CLT? In the CLT we have a sequence. We have a sequence of random variables. Where is the sequence here? We see that we have just a single random variable x. So x is binomially distributed, and we don't see any sequence here. But so we can say that x. What is x? What is the physical meaning of x if x has the binomial distribution? So x is a number of successes in a series of Bernoulli trials. So if x has the binomial distribution with parameters n and p, that means that x is a number of successes in a series of Bernoulli trials with number of experiments, number of trials equal to n, and probability of success in each single trial equal to p. So we can say that let us introduce random variables x1, x2, x3, x4, and so on up to xn, such that xi is equal to 0 if there is a failure in the ith trial, and equal to 1 if there is a success at the ith trial. So xi can take only two values, either 0 or 1, and it depends on whether the ith trial was successful or not. So 0 for unsuccessful trials and 1 for successful ones. And so if it is so, if we assume that there is this sequence of random variables, a set of random variables from x1 to xn, we can say that our x that has binomial distribution is equal to the sum of these xi's. So as x is number of successes, and each xi is equal to 1 if there is a success and equal to 0 if there is a failure. So when we add all xi's, we'll get what? We'll get number of successes. So we'll get x. So we can consider x as a sum of identically distributed independent random variables with finite expected values and variances. And so that is why we can apply the CLT to x. And that is why we can state that so this formula is true, so that x converges in distribution to a normally distributed random variable. And so the meaning of this theorem, applied, meaning, is the same as of the previous one. So if n is big enough, then we can replace the binomial distribution with the normal one. So we can say that a binomially distributed random variable is actually normally distributed if a number of trials is big enough. So the last question is, so what do we mean saying big enough? So if 100 is big enough or not, or 1000 or 10 or 50, so the answer is that in most cases, several dozens is enough. So it is enough for n to be equal to several dozens to apply this theorem. So sometimes they say 30, so that there is a magical number, 30, and so if n is more than 30, then you can apply the CLT. Actually, it depends on the distribution of these xi's. So for some distributions, we really need several dozens of x's to apply the theorem. For some distributions, this critical n is even lower. So for some distributions, for example, n equal to 10 is quite enough to apply the CLT. So, and now it is time to show you several examples. So, de Moivre-Laplace theorem is applied when the only alternative is multiple applying the Bernoulli formula. So, when the only other way to solve the problem, to find the probability we need to find, is to apply the Bernoulli formula many times. So let us consider the simple example. Let us say that we are asked to find probability that number of heads in 1000 flippings of a coin will be from 495 to 513. So x, let x be number of heads in 1000 flippings, and so they say find probability that x will be from 495 to 513. So we see that x is a number of successes in a series of 100 Bernoulli trials. So x has binomial distribution. If we deal with the number of successes in a series of Bernoulli trials, we deal with the binomially distributed random variable. So that means that x has binomial distribution with parameters 1000 and 1/2. So 1/2 is the probability of getting heads, probability of a success in each single trial. So we can say that as 1000 is big enough to apply the de Moivre-Laplace theorem. So n is equal to 1000 is big enough to apply the de Moivre-Laplace theorem, and to assume that x has normal distribution with parameters np, that is 1000 times 1/2, and n times p times 1 minus p, so that is 1000 times 1/2 times 1 minus 1/2, that is 1/2 also. So that means normal distribution with parameters 500 and 250. So after we assume this, we say that probability that x is from 495 to 530 is phi of 530 minus mu minus 500 divided by sigma by square root of the variance by square root of 250 minus phi of 495 minus 500 divided by square root of 250. So this is if we simplify these numbers and express them with a decimal number, so we'll get minus 0.32 and 0.82. And so the values that we can find in the table of the phi function are I'm sorry, not so. Let me do so. So this. So phi of this is actually phi of 0.82, and phi of this is phi of minus 0.32. And so this is 0.7939 minus 0.3745. 3745. These are the values from the table. And so finally I get 0.4185. So this is the answer. And what is the alternative if I don't apply the de Moivre-Laplace theorem? The alternative is to deal with the binomial distribution with the Bernoulli formula and to calculate probabilities of all values between 495 and 530 and to add them. So the alternative is to say that probability I'm asked to find is actually a probability that x is 496 plus probability that x is 497 and so on up to 512. And so these probabilities are to be found with the Bernoulli formula. So the first one is 1000 choose 496 times 1/2 to the power of 496 times 1/2 to the power of 504. So, and this is only the first probability. Only the first. And then I am to do this, so 18 times. I am to apply this formula 18 times for all these values, the Bernoulli formula. It is very just not difficult, but it takes a lot of time. It takes much time to find the probability of this kind. So that is why when we apply the de Moivre-Laplace theorem, it fastens the calculations very much.